This is EE300 Fall 2016, Module 3, Video 1, Network Functions. In this video, we want to look at a couple of circuits we've used previously to set up the story we're going to tell today. We want to consider the case of what are zero state response inputs, that is, inputs that yield zero state responses. We want to introduce the definition of network functions. We'll have two different kinds of network functions, transfer functions and driving point, either impedances or admittances. You want to see how you find the output of a circuit when you're using the network function. And then we'll summarize what we did here and look to future videos. So let's review a couple of familiar circuits. First of all, conceptually, we know we can separate the response of a circuit to a voltage input source, voltage source or current source, into a zero state response, which is what the circuit would do if there was no energy stored in it, and you only get the response to the drive, and a zero input response, which is what you would get if there was no drive and you only had what was in the stored energy, the response due to the stored energy. So here's the familiar series RC circuit with the voltage source input and the voltage across the capacitor as the output, V of t. We know that we go to the S domain. We could do voltage divider first to find, we treat this as a superposition problem, so we look at the response due to the voltage source and use voltage divider, impedance of the capacitor over the resistance plus the impedance of the capacitor. And then when we're looking at the voltage across these terminals, the V of S terminals due to the internal stored energy source VC of 0 over S, that's the same as the voltage across the resistor. This is acting like a short, the source voltage there. So we get R over R plus 1 over SC times VC of 0 over S. And then we go through our familiar extra two steps. One where we clear out the denominator and end with a trailing term usually of 1 in the denominator polynomial, and maybe do some cancellations. And then we divide by the coefficient of the first term of the, we factor out the lead term, so we get a coefficient of 1. And of course, we have to do that in both the numerator and the denominator, so we end up with this expression for the zero state response, which is proportional to the drive input in the S domain. And then we have the zero input response, which of course is proportional to the strength of the stored energy, VC of 0. Square root, VC of course would be the square root of the stored energy. We have this parallel RLC, not quite parallel, not quite series RLC circuit. We have the capacitance in parallel with the resistor in series with the inductor here, and we're driving it with a current source, and we're interested in the voltage at the terminals we're driving it at. So this is a driving point situation. Again, we go to the S domain. We have the initial condition of the voltage in series of the capacitor in series with 1 over SC, the impedance of the capacitance. We have IL of 0, the initial current of the inductor over S, in parallel with the impedance of the inductor SL. And then again, we do a superposition problem, treating each of these three sources separately and using resistive circuit techniques. So for the drive due to the input current I sub S, or I of S, we have, again, the voltage source is turned off, so it's a short. The current source is turned off, so it's an open. So we have 1 over SC in parallel with R in series with SL, which is this expression here in the top expression. The voltage due to the voltage source here would then be the voltage divider of the series R plus SL in series with 1 over SC. So we get R plus SL over 1 over SC plus R plus SL times VC of 0 over S. And then the voltage due to the current, to the IL of 0 current source. The current's coming down, it's going up through this impedance over here, so it's against the polarity of the VS here. So we're going to get a negative due to this. And then we find the current up using current divider, which would be SL, the other impedance, over the sum of the impedances, 1 over SS, 1 over SC plus R plus SL, times the impedance in question, 1 over SC, and then times the source strength, IL of 0 over S. We do our same multi-step process, clearing out denominators to get trailing coefficients of 1. So we end up with these expressions here. We've done this before, so this shouldn't be too novel here. And then we divide out, factor out the leading coefficient of LC from numerator and denominator, and we end up with these expressions. And again, we recognize the first term as a zero state response, and the second two terms superposing to be the zero input response. So what kind of inputs result in zero state responses? Well, if the input's 0 for t less than 0, there's no way to store energy in the circuit up until that time, and any energy that was in the circuit a long, long time ago has been dissipated by then, assuming it's a passive circuit and only made up of R's and L's and C's, or made up of R's and L's and C's and amplifiers, but designed such that it does not inject net energy into the circuit. So anything like a unit step or an exponential times a unit step, this could even be a growing exponential times a unit step, doesn't have to be decaying exponential, cos times a unit step, exponentially enveloped cosine times unit step, sines, etc. Anything with a u of t in it is going to be a zero state response input. So you're not storing any energy in the circuit prior to t equals 0, which means that the initial conditions of all the energy storage elements will be 0. So Vc of 0 will equal 0, IL of 0 equals 0 for any capacitor, for any inductor in the circuit. That means there's no zero input response, so the output is purely a zero state response. So in the case of our RC circuit that we've looked at already, if the input is 0 for t less than 0, the capacitor voltage at 0 is going to be 0. That means there's no initial condition source in the circuit. We only have the impedance of the capacitor in the S domain. And so now it's simple. We do the voltage divider 1 over SC over R plus 1 over SC, and then our two steps, and there's our output in terms of the input and in terms of the divider network between the two. For the RLC circuit we looked at earlier, again, the current over here is 0 for t less than 0, so there's not going to be any charge on the capacitor. There's not going to be any current through the inductor at t equals 0. So the initial condition sources of the voltage source in series with the impedance and the current source in parallel with the impedance go away. They're not there, and we're left with simply finding the impedance of the network looking in. So we have 1 over SC in parallel with R plus SL, again, times I of S, and we go through our two-step simplification process to end up with, it looks like there's a missing IS in each of these terms here, folks. So this should also be times IS, and this should also be times IS. I think you can see where this story is going. So a network function is the ratio of the output in the zero state in the S domain to the input in the zero state in the S domain. They're called by many system functions. We call them network functions when they're particular to electrical circuits, electronic circuits. More generally, you can have system functions describing any system described by differential equations. They're sometimes denoted by H of S. They're usually denoted by H of S. Some authors use T of S, and in both these cases, we're talking about a transfer function. We're talking about the difference between the input, the ratio of the output at one port or a terminal pair to the input at another port or terminal pair. When you're at the same port or terminal pair, then you denote this by Z of S or Y of S, depending on whether it's a driving point impedance, that is voltage over current, or a driving point admittance, which is current over voltage. Again, this is when you have the input and output at the same terminal pair. We'll look at both these cases. You can use your impedance, which means resistive circuit techniques. And again, there's no initial condition sources in any of these. So in some ways, our problems got a lot easier. So here's our RC network. We've already found the voltage divider here between the impedance 1 over SC and the series R in series with 1 over SC. So to find the network function, we just divide the output by the input, which leaves us with the divider network 1 over RC over S plus 1 over RC, just the voltage divider itself. So that's called the transfer function because it's the ratio of the output at one port. This terminal pair here, we call it the terminal pair port. And it's a little more specific than that. The current going in has to be the same as the current going out of a terminal pair to be a port. We're not really interested in that right now. And then the input over here is at this terminal pair, Vs of S, and we take the ratio of the output to the input. That's what makes it the transfer function. And since this is a voltage, the outputs of voltage and the inputs of voltage, this is going to be dimensionless in our case. Transfer functions don't have to be dimensionless. If we'd been measuring a current over here, we would have a current over a voltage, so we would have units of conductance. Or if we'd had a current source in and a voltage out, then we'd have units of impedance. But they're not, it's not an impedance, it's what's called a trans impedance or a trans conductance or a trans admittance. We can talk more about that later. For our RLC network, we're driving with a current source and we're measuring the voltage at the same terminal pair at the same port. So in this case now, we have, again, the divider. We have the ratio using the parallel R in series with SL and parallel with 1 over SC. We've already computed this ratio here. So we divide V of S by I of S. That's going to be an impedance Z of S. And we call that the driving point impedance of the circuit over here. For every unit current in the S domain, what voltage do I get out in the S domain? And of course, that's going to have dimensions of ohms. R has units of ohms, SL has units of ohms, 1 over SC has units of ohms. So this ratio of V to I at this terminal pair will have dimensions of ohms. If we were to swap up for this network, if we were to swap this out and put a voltage source here and measure the current going in, right, we would expect to get the same thing except inverted, and we can work this through. We apply the voltage over the impedance 1 over SC. So that's just going to be Vs divided by 1 over SC, or SC, the admittance of the capacitor, times Vs, where SC, admittance is an inverse of impedance. And then the admittance of the R plus SL then would be 1 over R plus SL. And those two currents are going to add to be IS. And then we just put everything over the common denominator SL plus R and do a little bit of algebra. And we see that we have the same thing we had before except inverted. That what was the numerator is now the denominator. We had 1 over C S plus RL in the numerator previously, and there we have C over S plus RL in the denominator. We have 1 over C S plus RL in the denominator, and we had S squared plus S R over L plus 1 over LC in the denominator, and now that's in the numerator, exactly as it should be. So a driving point impedance and a driving point admittance are arithmetic inverses of each other. Or you can multiply the two of them together to get 1, however you want to think of that. It makes sense. We've got the voltage and the current at the same terminal pair. So whatever the impedance is here, the admittance ought to be 1 over that. Can you do that with transfer functions? So anyway, we've already worked through this here. I got ahead of myself on the slides. So here's the, can you do this for the transfer function? We saw previously when we had the input over here on the left of this network and the output was on the right across the capacitor that we had the transfer function was 1 over RC over S plus 1 over RC. If we swap the roles and put the input voltage source on the right across the capacitor terminal pair and look at this open terminal pair over here for V of S, we see that the output is just going to be the input because this is open, there's no current through the resistor, so the voltage is going to be the same as the voltage across the impedance of the capacitor, and those are the same as the impedance of the input, or as the voltage of the input. So in this case, the transfer function is 1, looking from input Vs of S to output V of S over here on the left, and that is not 1 over the H of S we found earlier. So the transfer function depends on which terminal pair is the input and which is the output. You have to be explicit. You have to know what your input is and what your output is. And it doesn't work the way it does with the driving point impedances and admittances. They're not arithmetic inverses of each other. And you can't just expect the input and the output roles to be swapped. So if you have transfer functions, how do you find the output of a circuit? Here's our RC circuit. Here's our transfer function, 1 over RC over S plus 1 over RC. The transfer function is the ratio of the output in the S domain, even though we've labeled it here on the circuit in the time domain, to the input in the S domain. And then we'll often do this. We'll draw the circuit in the time domain, we'll indicate it in the time domain, and yet we'll do our calculations in the S domain because we don't have to worry about initial condition sources anymore. The architecture of the circuit, the topology of the circuit is going to look the same. It's just whether we call that C or whether we call that 1 over SC. And that's not an excessive amount of bookkeeping to keep up with. So we know the output in the S domain is V of S. We know the output over the input is 1 over RC over S plus 1 over RC. So let's see, we have some specific examples here. So we had a 500 ohm resistor and a 1 microfarad capacitor, and the input is 10 e to the minus 1000 t volts. U of t, because the input is 0 for t less than 0 to get 0 state response. So our RC is 500 microseconds, and 1 over that is 2000. The transform of 10 e to the minus 1000t is going to be 10 over s plus 1000. So when we put that in, we just multiply the transfer function 2000 over s plus 2000 times the input 10 over s plus 1000 to get the output in the s domain. You know the ratio, the transfer function is the ratio of output to input. So to get the output, you multiply the transfer function times the input. And then it's just a matter of doing partial fractions. Cover up s equals minus 1000, amplitude 20. Cover up amplitude s equals minus 2000, amplitude minus 20. And so the time domain for t greater than or equal to 0 is 20 times e to the minus 1000t minus e to the minus 2000t. Nice that this is equal to 0 at t equals 0, and it's a zero state response, and it's a capacitor, so we know the voltage ought to be 0 over here. Because it's a zero state response, we know that the output was 0 for t less than 0, so we can put this all together and put a u of t here. In fact, we could have done this without going through this extra step of piecewise description of the output. So there's where we get to the point now where we can say why some authors would say that the Laplace transform includes u of t and assumes that the input, that the signals of interest are always 0 for t less than 0. We know that's not the case. That's not how you set up initial conditions on voltages across capacitors or currents through inductors. But for the zero state response, it is the situation. And so you can pretty much always include a u of t in your expression for your output when you're talking about zero state responses. We can look at the voltage across the RLC circuit. Here again, it's drawn in the time domain, input in the time domain, output in the time domain, but the driving point impedance that we found earlier is in the S domain. So we have a Z of S between these two terminals, even though they're shown in the time domain. And so the output voltage, V of S, will be Z of S times I of S, where Z of S is our driving point impedance as found earlier. Let's use these parameters we've had previously, 12 ohms for the resistor, 1 Henry for the inductor, and 0.01 farads for the capacitor. And let's look at the unit step response of this circuit. Just put a unit step of current, turns on at t equals 0 and stays 1 amps forever. After that, R over L is 12, 1 over LC is 100, 1 over C is 100, and in this case, I of S is 1 over S amp seconds. We plug these all in. We do our part, we find our roots and do our partial fractions. We've already seen that this can be done by completing the square. So we have S minus 6 minus J8 and S minus 6 plus J8. That ought to be a plus 6 there. That ought to be a plus 6. The root is at minus 6 plus J8. The root is at minus 6 minus J8. So these ought to be pluses in this third line here. Regardless, and I'm confident that these are the numbers I used when I did the partial fractions and actually worked it out. So the amplitude, you have a 12 times a u of t for the response, the constant part of the response, the drive part of the response, the forced response, and then you have your transient part of the zero state response. You take the real part of the root at the positive imaginary part. So the real part of that is minus 6, multiply it by 2 to get the cosine term, and then you have a root at minus 6, so this ought to be S plus 6, so e to the minus 6t, and the root is at J8, so you have cos 8t. And then you take negative twice the imaginary part, so instead of having minus 7 quarters, you have minus 7 halves, which is 3 1/2, and minus that is going to be, minus twice that is 3 1/2, so you have 3 1/2 e to the minus 6t sine 8t, and all of that will be u of t, so there's no voltage for t less than 0. You want to do magnitude and angle, you take the magnitude of the residue there, and that's 12 1/2, and then you take the angle of that, which is minus 163.7 degrees. So it's almost 180 degrees, and you can see it ought to be, because you're going to get that minus 12 out at t equals 0. So when you get to t equals 0, you ought to be getting close to minus 12, and so you need that being close to minus 180 degrees. That's what you expect. It's an underdamped circuit. It ought to have some oscillatory stuff that decays away, that's invoked because of the energy sloshing back and forth between the L and the C, but it's damped by the R, so every time it sloshes back and forth, a little bit of it goes away, giving the exponential decay. The long run, as t goes to 0, the exponential goes to 0, and you just get 12 volts out, which is what you'd get with the inductor acting like a short and the capacitor acting like an open, and 1 amp over here and 12 ohms there. So in summary, we can the inputs are 0 for t less than 0. We're going to get 0 state responses. We call those kind of inputs that evoke 0 state responses ZSR inputs. The ratio of the 0 state response output to the 0 state response input in the S domain is the network function or system function. Notice these were not ratios of time domain functions. These were always ratio of S domain functions. We drew circuits in time domain because that's the world we really live in, but the ratios are in the S domain. If we take the ratio of an output at one terminal pair to an input at another terminal pair, that's a transfer function. If the input and output are at the same terminal pair, we call that a driving point impedance or admittance, depending on whether we're talking about voltage over current for impedance or current over voltage for admittance. The driving point admittance and the driving point impedance were inverses of each other, but it didn't work that way for transfer functions. You can't swap the role of the input terminal and the output terminal and expect to get an arithmetic inverse of transfer functions. And to find the output, we would multiply the network function by the S domain input, and that would give us the S domain output, and we would inverse transform. So next couple of videos, we're going to look at finding the input-output differential equation from the network function. We can actually go back, find our differential equation, and even impose initial conditions if we wanted to, given other knowledge. And we can also, we'll start to talk about impulses finally, and what the impulse response of a network is. Then we'll go after that to step responses and sinusoidal steady states. And then we'll start talking about designing stuff. This has been EE300 Fall 2016, Module 3, Video 1, Network Functions.